Alright, then we'll get into chapter 15. So that's your impulse and momentum. So first, we'll get into linear impulse and momentum. Of course, we're always studying the particle anyway. And then, yes, we'll take into account for your force, velocity, and time, always, yeah? And then we'll do your conservation of linear momentum for particles. And then impact, of course, and then your angular a little bit, impulse and momentum, but we won't get into that in details. And then study a little bit about the steady fluid systems and your propulsion, yeah, for your variable mass. So let's see one by one. So before we get into linear impulse and momentum, you need to review your force, which is your mass time acceleration, yeah? And your acceleration is a change in velocity over change in time. You can also sum up your forces because you're gonna have a different velocity. Okay. So anyway, about that much you have to review your force. Okay, so last chapter I mentioned of mass and velocity. I call it momentum. Yeah, and you already understand what momentum is, and that's just like we're studying when the mass is moving with a velocity, we call it momentum. Yeah, so in mathematics you just multiply the two quantity and you're going to get the magnitude of your momentum. Yeah, and your mass is positive because it's a mass of a particle, and it's a vector for velocity, so you have a direction. Yeah, unit mass is kilogram and SI, meter per second for your velocity. Your foot-pound mass is slug, and then your foot rate divided by second is your velocity, which is feet per second. Yeah, so that's your SI, and this is your British system, and this is our momentum. We calculate the magnitude of momentum by multiplying mass with a velocity, yeah, because your mass is going with a velocity in that motion linearly, yeah, in this case. For impulse, we're studying the force on that particle, yeah, with the change in time, yeah. So we're carefully looking at the force, right, during a period of time. So what is the effect of that force on the environment, yeah, and we call that impact, yeah, oh sorry, impulse. So impulses, we're studying, yeah, again the force, and we're taking a look at that force in a time, yeah, and think about, oh, what is the effect, yeah, of this, how this force is acting, okay, and that's what we're looking at during our time, okay, during our time. Pay attention, okay, there's no and nothing but your particle, because your particle is inside of this force, because you know force is a mass time acceleration, yeah. That's the reason why, don't forget, your particle is represented in terms of the force right here. There is the particle when we deal with the impulse, yeah. And then even though we ditch calculus, you still have to know the change in time, yeah, from time 1 all the way to time 2, and then you have your force, and then of course and then your change in time, yeah. So C, we're talking about the constant force. When you see the little subscript C right there, yeah, because the force is constant, time going from T1 to T2 in that interval, yeah, and your impulse is that, yeah. But we're gonna use this more than this, yeah, so you will be concentrating that second expression, yeah, but it's actually the same anyway, yeah. Your unit of your impulse is your Newton in second, that's in British system, is pound, and then times your second. So you have your impulse, your force, your initial time, and your final time. Yeah. My dog is asleep and snoring in the back. Okay, so here is the impulse tool. This guy is using that tool to remove the dent. Yeah. In the trailer fender. So he drilled a screw in a hole. Yeah, in that fender, of course. So make a hole, right, using this little screw and then drill it into the fender. So what this guy is doing, and then the weight is, of course, a jog upwards. And this is your stop ring, okay? So it's gonna just come right up, like as you pull it. So impulses, we're studying the force, okay, in that time interval. So what it does is like the impulse will get transfer right in along that little shaft right here of that screw. Okay. I would just say like a tool because there's a modification here, and pull suddenly on that dent. Yeah. So that's how they remove the dent from the trailer fender. It was just talking about, a simple way is that you're making a force, yeah, and you're making that force during that time, and you have the impulse because it affects, yeah, on this fender to fix that dent, okay. And what's the amount of the force is going to be this amount in that time, and you get that much of impulse, okay. All right. We are very accustomed to call the impulse like impact, okay? Because it's kind of like a fast transferring, yeah, of force. Because when you, and don't forget to pay attention when you write this little t, we're talking about a tiny little minute, time interval. So the force is really fast, right? Happening very fast. So when you read the equation, make sure you know what you're reading. Yeah, you're dealing with a little time, so you can be able to understand how fast, right? The impulse can be, and that's why we call it impact. The effect of the force on the environment. All right, and of course you can be able to study different momentum because your particles moving with different velocity anyway. So I always have like a MV1, MV2, yeah, two different velocity of the same particle, yeah, because it's moving with different velocity. So you have a momentum 1 and momentum 1 and a momentum 2. Of course, you can calculate that, you know, so when you look at it, this is your impulse. So the sum of the impulse from time t1 to t2. Pay attention how I am reading. So here I define the impulse. That's the sum, and we're going from time 1 to 2, and we're going with the two different velocities. See? So therefore, you're going to get, if you simplify it, yes, your impulses again can be written in this way. Your constant force, right? T2 and then T1, and then you go in and multiply that. Yeah, and you know that your and this is your impulse. Yeah, so impulse, yes, and I'm going to put it into here. I put this equation into here, so I translate the whole thing as I for impulse. So I have my MV1 here and MV2 there. Yeah, so I can be able to write it in a non-calculus conceptual expression like this, easier for you. Yeah, so if I want my impact for this, right, sum of impact, which is this, and or we can call it total impact, you're going to get the mv2 minus mv1 here. So your first momentum is subtracted from your second momentum, and you're going to get the sum of your all the, yes, resultant impulse. Okay. Of course, it has a little diagram. You can be able to see your initial momentum diagram. Then you have your final momentum diagram, and here is your impulse diagram. Okay, meaning like we are studying the effects, right? Apply force in that little time to this particle moving with a momentum. You are going to get final momentum, yeah, because you have a disturbance, which is an impulse coming into this moving particle, and it's moving with a velocity v1, yeah, and you have a force, and we're going to give it to that particle the force in that little tiny amount of time really fast, yeah, so you get your particle is now getting a different velocity, meaning going with a different momentum, different from the first momentum, yeah, so that's what it's talking about, the whole equation. So try to describe or translate the equation into the meaning, yeah, very important. Don't just remember the equation. You should be able to write the equation by understanding the situation, okay? This is just for you to take a look at it. I'm not going to ask you, already told you several times, we're not going to get into the coordinates, yeah? So we don't have to branch out your XYZ components of your impulse, yeah? Because we can branch your force into XYZ components. Of course, we can also branch our velocity into XYZ because they're all together anyway, yeah? Okay. Of course, your golf, and this is your impulse, yeah? You have a force in a very, very minute amount of time and hit it. Your golf ball is gonna just shoot off, right? Usually from the position, which is resting position, and you're gonna give it a really fast acting force, your impulse, in a particular time, and you're gonna get this golf going, yeah, golf ball going. So we definitely use the principle of linear impulse and momentum to explain the movement of the golf ball, right? When you're striking it. Okay. Then we get into linear impulse and momentum for a system of particles. Again, this is just for read. Yeah, I wrote it here, read only. And you have, of course, your different, see, like your impulse right here. Yeah, this is just telling you from this time to that time. I have a initial impulse and I have a final impulse, right? You can also use it vice versa, and you're gonna have different, see, different effects on that particle motion, yeah. So here, look at that, little particles go in different directions, yeah. Of course, we're dealing with here the inertial coordinate systems, but again, this is for your reading only, but explaining relatively the same thing but applied to a system of particle instead of a single tiny particle, yeah, tiny or big, whatever. So your impulse here, your time, and then there's your first momentum, a sum of momentum, because you're dealing with that many particles. See, I is infinite, and you can count as many as you want. You can go from 1 all the way to wherever you want to cut off, yeah, and then the sum of your second momentum. And don't forget that even though we draw like 1, 2, 3, 4, 5, 6 particles, you have a gazillion, billions and billions of particles in the environment. Again, seen and unseen, yeah? So if you think about how many, oh my god, that's a lot. Populated, yeah? Crowded. Okay, procedure for analysis. Don't need it, just read through. It's a whole bunch of review anyway, yeah? But this is your pitching machine rotating, of course, and you have two wheels when you think about the rotation. And here is a little, yeah, a bar, and it's been subjected to the friction. So you have your frictional impulses. Impulse is nothing but it's just a very abrupt force, right? In a unit of time, and you are dealing with that impact or effect on the environment, yeah. So here this ball get a linear momentum because the ball itself is a mass, and is gonna get the velocity because of this wave impulse, yeah. So you have your frictional and also normal. Normal is everything that's subjected to 90 degree to the particle. We'll call that normal impulse, yeah. So the wave impulse is constant, very happening in a very small amount of time, delta t, yeah, which is in contact with your wheels right here. All right, 15.3 is your conservation of linear momentum, yeah, and again you're dealing with the system of particles. So I will not ask you, all you have to know is a conceptual meaning of it. Yes, so just showing you your momentum, yeah, is equal to the sum of your momentum of many particles, yeah. Here you just say like many particles like that. Why? Because the sum of that many particle going with a velocity is equal to the sum of that many particle going with a second velocity. Yeah, they conserve. Meaning that if the second final one is the same as the first one, right? After it has some sort of impulse, but they're the same, meaning like you get the total sum the same thing, so therefore it's been conserved. Yeah. It doesn't have a distinct change because they always balance it out. Doesn't matter how your velocity is changing, yeah. So that's what it's saying here. So telling you that the total linear momentum for a system of particles remain constant, the same during the time period going from 1 to 2, yeah. So why are they same? See, so pay attention. There's no impulse, or the impulse is 0. Yeah. So I want to show you a review again. So pay attention when you're looking at it. See that impulse right there? This, I'm going to copy it. Yeah. Go down all the way down to here. And I'm going to stick it right in here for you. Yeah. So this part, right, is 0, and that's what it's saying. And instead of a single particle, we have like a system of particles, yeah, I representing. The rest of them are the same, yeah. So make sure that your impulse is 0 at that time. You have a conservation, yeah, of your total linear momentum, and that's what's talking about. Okay, several examples right here. So the very first one is the hammer in the top photo. Yeah, this guy, of course, applies the impulsive force to the state because you're hammering it down, bang, 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 yeah, in a very small unit of time. So the contact, right, the weight of that state can be considered non-impulsive because that state is driven into the soft ground, yeah. And then don't forget your Newton, yeah, law, because you have one particle, your ground is a second particle. They have forces acting on each other. They are attracting to each other, yeah. So they cancel out, and so does your impulse, yeah. So we consider it's non-impulsive even if the weight of the stake is going straight into the soft ground, yeah. And then the stake, of course, is acting on the ground, and the ground is acting on the stake, and we consider that non-impulsive. Why? Because when you study the effect of the impulse on the environment, your environment is non-stake and the soft ground. Here is you have a hard ground. That's the second picture, yeah. So it's a concrete chipper. We're breaking the concrete. Now you also have the impulse forces, right, coming out from this motor applying into that stake, into the ground, which is a hard ground right now, which is concrete, yeah. So now you have a two impulsive impulse forces. One is above the ground because it's this top, right, your chipper, and the other one is your concrete ground, yeah. And you must always remember, I have told you many times, there's force, attractive force between any two particle. That's your particle, that's your particle. This is your particle, and that is also your particle. That's your particle, and this is your particle, right? Everything is a connected system right there. All of it being affected by this. Don't think like you don't have an impulse on yourself by this. Don't think like the impulse is only, to your concrete ground. Your impulse is also at you, okay? Because you're holding it anyway. It's just like we usually ignore it, yeah? The same thing with your tennis racket and your tennis ball. Yeah, your impulse right there, like really quick force happening in a very, very small amount of time, strike it, bang, yeah? Um, you're gonna have this ball is gonna have a different velocity, yeah. So before the velocity one, after the impulse, you're gonna have a velocity two, yeah. So we always go back to our impulse equation, yeah. This is what's happening. Something moving come and strike to this tennis racket right there, bang. So racket is gonna give the ball a rough or a fast acting force on it. So the velocity of that ball changes into v2, and that's what you're seeing right here in a slow motion, of course. Yeah. All right, you got it, I guess. All right, procedure. Just read, and go all the way. This one, 14 and 15.4 is also reading. A whole bunch of your calculus in it. So 15.4 is this one, yeah. So I will pick some of the preliminary and fundamental problems for you. So you just read for now, and we will get back to it when we do the problems, yeah. So I'll give you a couple of examples what to do for your chapter 14 and 15 problems, yeah. Then we will get into a little bit on your angular momentum. When you think about the angular momentum, you always have to think about a point because it is angular in nature, so it will be rotating anyway, yeah. Direction, you have to pay attention. So there is a point, and we call it just O to measure stuff against that, yeah. And moment of the particle linear momentum about that point O, because we want to take a look at the angular momentum about that point O, okay. So the angular momentum is nothing but the moment, yeah. We're just looking at the moment of your that particle's linear momentum about the point O. So what is the moment? You have to know. So moment is just an instant, right? Your momentum happen in that instant. Your symbol is here, yeah. H. This is your point O. That's your x z, because you are subjected to right now 3 axes, x, y, and z. It's really difficult to explain angular momentum without the axis, yeah, in your coordinate axis. So here, so this is what z is your axis, yeah, where your O is meeting your other x and y. So anyway, and your d is this, yeah, distance from O to the direction of that particle, yeah, momentum, which is your m, your particle mass, and then v going with the velocity in that direction, and which the line of that direction is away from d about that distance, yeah, d distance, and then mv. So be careful with all the symbols, yeah, it's very confusing for you because they're the same anyway. So you have like a change in time, it's a d, little tiny change in time, we use a little d, but this one is a different d, yeah. This isn't the change, this is representing the distance from O, yeah, to the line of your momentum of your particle. Your z is your z-axis, and m is your mass, you know that, and v is your velocity of particle, you know that too, and your d is the only thing, yeah. So informal definition is your moment arm, which is this. Your moment is just an instant of that particle, is a linear moment about that O, okay, point. So this moment arm is your perpendicular distance from your O, point O, to the line of your action of your particle's momentum, yeah. Unit, you're dealing with the mass, the kilogram. You're dealing with the velocity, yes, so meter per second, and you're dealing with a distance, yeah, which is this distance, so another m coming in, so that's your meter per second, and then your kilogram. altogether with fuses. So kilogram meter square per second is your angular momentum unit in SI. For British system, you got a slug times a feet square per second. Okay, feet for the distance, feet per second for the velocity, and then slug for your mass. It's going to give you the moment. Yeah, moment of momentum is called the angular momentum. Yeah, moment of, actually this is linear momentum, is equal to the angular momentum. Yeah. Then we apply a little right hand rule. So you have your thumb right there, direct upwards in this example, perpendicular to the plane, which is this guy, along the axis. Okay. So the thumb is pointing along the z axis. Yeah, the plane is right down there, and it is perpendicular to that plane. And that is your right hand rule. Yeah. So what's the right hand rule do? So it does show you the direction of your angular momentum. Yeah, the angular momentum of that particle is right up on the z-axis. Okay, so you have your angular momentum is equal to our simplified version of equation, position factor, right, which is this guy. Yeah, we're measuring from O to there, the line of your momentum of your particle, and we call it R here, D over there, but R here, and times mass times your velocity of that particle, which is this guy. Yeah? So just saying like this guy is that distant away from this measure point. Yeah, and of course you are having a angular momentum. You use your right hand rule, and thumb is going to go to this direction because your plane of motion of your particle is on that side. See how it changes. So again, this thumb got to be perpendicular to your plane of motion. Yeah. And of course, we can also express in your Cartesian components like that, but we will not be calculating in a Cartesian components way. All you have to deal with for your course is this. Yeah. Okay. 15.6 is a relation. You're looking at that relation between the moment of a force and your angular momentum. Yeah. So here, this is a velocity in vector form, a little dot right there. Sometimes we put the arrow, sometimes we put the dot right there. It's just showing you the moments, like moments about point O, yeah, of all of your forces. So you see the sum of forces acting on that particle, and you can relate that to the particle's angular momentum, yeah, and you can apply this equation. So this is your angular momentum, your mass, and then your velocity, of course, and we call this a little dot, the whole thing, yeah, as your angular momentum, even if this is again your velocity. Okay, velocity is a vector. Yeah, I don't know why we usually use a dot, right, when you deal with the velocity, especially in the momentum cases, angular momentum cases, just to be different, I guess. So the sum of your forces right here, and we have this. Okay, now we're going to branch into moment of the force. So instead of angular momentum like that, we're going to bring another symbol as moment for m. Yeah, the same thing, sum of your moments, yeah, of your sum of your forces is equal to your r, because your distance from your O to the plane of your motion, and that's your sum, yeah, equal to r times nv, little dot right there. Okay, that's just a momentum, by the way. You don't have to feel so bad to look at a different symbol. They're just symbol. Yeah. And this we have an equality right here with your sum of the force and your momentum, and we just plug that into this formula. Yes, and your moment is defined by the sum of the forces times your distance, okay, from your reference O. and we plug in this, link it to the angular momentum like that. Yeah. And again, I'm not gonna go into calculus, but you will use just a simplified version of the equation. Yeah. So again, we won't do the derivative right there, but it's okay. It's just showing you the change. So you will concentrate in here. Yes, r dot times. This is just a vector mv, and then r times nv, yeah, another vector velocity. So your so again, don't worry about calculus part, yeah. So you would just concentrate. Probably, I will ask you only up to here, and the rest of them you can just read because we're getting into the system of particles right there, yeah. But if you know, like the moments of the forces, or the sum of the moments of the forces, which is this guy, yeah, about the point O is equal to the angular momentum, yeah, and that's pretty, I think, cool for you now, yeah. So yes, 15.6. I just want you to get this slide and don't worry. Uh, yes, I want you to get this, yeah, simple formula, and don't worry to getting into the system of particles, yeah, for now. Just read it. So that would be this, yeah, for your textbook, yeah. If you can just read it, and know that the sum of these moments, yeah, about point O for all of your external forces acting on that system of particle is equal to this guy, which is a change of your total angular momentum, yeah. About that point anyway, our measure point is O anyway. So if you know that, yeah, that would be cool. You know that, right? This is the sum of your moment, and that is the total angular momentum, yeah, which is this, yeah, total angular momentum. Okay. Then, so resultant force, right? We write it again, each rating, and is equal to the your particle's linear momentum, yeah. And we can write the momentum is nothing but your mass and velocity, so we can put that into back here again, yeah. And you will get the same thing for your systems of particle, which I already showed you, and I wrote this back here again. That's the your angular momentum, yeah. The sum of it, because you have like the I, this I mean like infinite, yeah, particles about that point. Of course, there are people who actually calculating these forces, yes. Like if you study like the nano level or pico level, then you're gonna go crazy, right? Studying the drug effects in your system or things like that, or producing the side effects, yeah, or the efficiency of a particular developed drug in a body system. So we can get about 40 to 60% efficiency of a drug. So you always have about 40 to 60% of side effect every time you take a drug, yeah. So you can be cured as well as you will be getting the side effects, but we trade it because their cure is has some more benefit than that side effect, meaning like the human body can withstand the side effects, yeah. So we trade that even if the efficiency for your drug is kind of is not the best value that we want it to be, yeah. So if you have like 80% efficiency in drug tests, of course you study these things, by the way, yeah. Why? Because at that level in the body system, the drug is going to be in a constant flow, right, with different velocity, by the way, hitting on different molecules and the protein inside of your body system. Yeah, we can go down our particle to that small pico level, nano level, all the way down, or as big as the stuff in the space. Yeah, and of course everything on the surface of the earth that we are studying, mostly cars and trains and planes. Yeah, major moving objects on the surface that matter to us. Your supply chain vehicles, and the vehicles that we are driving, riding, everything. Why? Because we wanna, human life is valuable and we wanna protect. So we calculate all kinds of stuff like this. So anyway, so let's go back. 15.7 is your angular impulse and momentum. Again, it's read only because it's a heavy calculus part in it. So I'm not gonna go into it. You can read it. We're dealing with just a time, of course, and interval, and we're dealing with the moments, and we're dealing with the angular momentum. And we branch it out again. So every time you see x, y, we're talking about the coordinates. And we study the forces in different axes, okay, and then sum it up. Sometimes we break it up, and but of course it's important for us to do it to tackle the problems of the world. Usually is to say because human life is very important in our perspective. Okay, human think that we're important. Our life is more important, than other stuff. Of course, anyway, so 15.7 is read only. Conservation of angular momentum conceptually, you have to know. You have to know that when you have your angular impulses acting on a particle, and they're all zero during the time, right? T1 to T2. And we have a conservation of angular momentum, so the sum here is equal to the sum over there. Why? Because your impulse, yes, is zero at that time. So we go back to the same equation. So remember your angular momentum, and when we deal with the linear momentum, we talked about the impulse right here. Yes, so this is your linear momentum, your L, and so your impulse when that is zero. So now we go all the way back to here, and here your angular momentum is equal to your other angular momentum, when your impulse affecting that is completely zero, meaning like there's no impulse acting on that angular momentum, so your before and after is the same thing, So the sum of the angular momentum, is equal to the sum of the angular momentum, your condition 1 and the condition 2, because our impulse is completely zero at that little tiny interval, time interval. Here you can see the angular momentum, which is going that way. Here, this is your, we can say the measure, okay, distance from your point of datum, and you have your sister right there. So this, you can see, look at that, that's each particle, so we have a system of particles, so we gotta pay attention to all of the momentum, or all the momenta is a plural of your momentum anyway, so all of the momentum of these particles, total momentum, you have to take into account. That's what it's talking about. So if you neglect the air resistant, meaning like air, when we talk about air, there's a gazillion of particles right in there as well, but we again assume neglected, and we're gonna take this amusement park right, so z-axis, that's my dog. Conservation of the angular momentum about that z-axis, and you have your rotation right there, So why do we have the conservation of momentum when we ignore the air resistance? Because you have a normal force acting and you have your weight, all right, parallel to that, and there's no impulse, right? Since there's no impulse, we've got this, okay? And that is called the conservation of angular momentum. The angular momentum is conserved because there's no impulse on these, we will call it the rider, right, and that amusement park ride as a particle, so there's no impulse acting or getting affecting these particles. Otherwise, you're gonna be sorry. You're gonna have to be so fun, right? If your impulse is acting on you, oh my gosh. Right now, just going with the very constant, because your angular momentum is balanced. Yeah, meaning like no impulse affecting them on that axis of your amusement park ride. Okay, procedures for analysis, just read. Yeah, we will hit again a preliminary and yes, example, easy ones. Yeah, so don't freak out. It's gonna be okay. What is this? This is just a video. Oh yeah, from your textbook. It's just showing you how your velocity and time graph. Yeah, velocity is fastest, so that's the x-axis, y-axis is your time. So as it goes up, velocity goes up, time goes up, and then you can be able to see the forces affecting on that car. Yeah, which is has a weight. Yeah, of weight. Okay, which is your mass of 1500, and then times your acceleration due to gravity right here from your z-axis of your reference point about 100-meter distance away from it. So this is why you can be able to feel your momentum, your weight, your force, and then your distance away. Yeah. Okay. Then we'll get into a little bit on 15.8. Yeah. So that just dealing with the fluid system. So we have a fluid stream here, and we're going to take a look at the steady flow of it. So when you see here, there's a flow of that fluid example, right? And it's going into the control volume. So this is going into this I would say it's not cylinder, it's kind of like a curved cone, right? And then coming out of it with a going in with a velocity VA, coming out with a velocity VB, because look at this, the geometry of this container. Yeah, a part of the container. We can't see the whole of it, but then it curves. Yeah, so when it curves, then of course the velocity would change. Yeah, the mass is of course a fluid mass here that we're dealing with. The particle is fluid, and we're studying the flow of it. Yeah, so here is your point, reference point, your distance, to the plane of your motion right there. Yeah, so here is your momentum going with a velocity and coming out with another velocity, in that container. You can see the sum of the forces. Yeah, and here the same thing coming out, and the time taken, time t. Here's your change in time, delta t, minute change in time, and we're just adding that how long it takes. Yeah, so we're gonna take it, if we want a steady flow, then the flow of that fluid going into the control volume got to be equal to the flow out. Okay, what is equal to what? So you gotta know that we call it flow. Okay, and we're gonna take a look at what flow is, but you kind of get it. Flow seems to be momentum of your fluid. Yeah, because when you take a look at it, you're seeing, look at that. Yeah, that's a momentum. We're seeing that this is your force and change in time. Yeah, your impulse. Yeah, why there's an impulse is because of the geometry of this structure. Yeah, whether your water or fluid is going into, that changes, and when that changes, you have some form of a force right there. Okay, but we're gonna call it steady flow. Yeah, if that flow in and flow out is the same, meaning like the impulse is not affecting the flow, at that time we call that the steady flow. Yeah, so flow here outside real life, this is just your conveyor. Yeah, something is moving. We're transporting some material here on this conveyor belt. Yeah, so going with some frictional force, of course you have it on it. and we want this material to travel on the conveyor belt. Okay, and here of course you have a change in the momentum is happening right there because of your geometry. See the conveyor belt geometry is changed right there. Yeah, straight down. So the gravel, this is it's a gravel material, is gravel streaming on that conveyor belt. It's going to travel along the belt, right? This is the last C of your previous example, just showing you the flow. Yeah, and your geometry changes, a big here and small here, your diameter. Yeah, and you have a different velocity, of course. And this is just showing you the differences in your diameter of that, okay, container. Okay, so here is just showing you the fan right there. Yeah, so the air on one side of the fan is at rest. When it passes the fan through the blades, right, of course you have momentum in it because the fan is going that way anyway. So the change in the momentum of the airflow, okay, the blades is giving you the horizontal thrust on the air stream. So you have a change in momentum when the air passes through that, okay? So when the blades of that fan, right, turn faster, then you're gonna also have the resistance, yeah? So that's come from your air, again, the opposite thrust, by the way, of the air on the blades. It's gonna overcome the rolling resistance of the wheels, yeah, on the ground. So you can be able to understand, oh yeah, there's a change in momentum because the environment is different. Yeah, the air outside of the fan is different from the air passing through the fan because we are making the stream of that air flow by rotating the blades of the fan. Yeah, so we're manipulating the momentum of the air because we want that air stream with a force, right, going through it. Of course, your air also have the opposite, of course, thrusts on the blades of that fan. Okay, so you can be able to understand like these things are going on. Yes, in this example, the fan and the air. So don't worry about the derivation here, yeah? So just giving you the derivation, but I only want you to get this, which is your Q, yeah? And that's just like measuring the volume of your fluid flow. Of course, everything we are dealing with the unit time, yeah? So per unit time. And we going to it is referred to as a discharge or the volumetric flow. Yeah, so if you could get Q is equal to VA, then I think you're gonna be okay. Yeah, and this A is just a entrance. Okay, just slide is moving. This A is just the entrance. Yeah, it's kind of like this. Okay, so you can be able to remember the entrance of the flow. And of course the velocity, yes, and this one is the volume of your fluid flow per unit of time. Okay, showing you how much distance, right? This is dm divided by dt. So this one coming out from here, which is from there. Yeah, so you can be able to understand just the mass, right? We're dealing with a change in mass and over a unit of time. Okay, that's your density and velocity and the cross-sectional entrance area. Yeah, and that's your density. Okay, talking about the fluid flow volume, so you can be able to understand, oh, at this time, right, during this time, that amount of mass of fluid pass through that entrance. Okay, with this velocity, and of course the density of that fluid is this amount. Okay, so that's what it is talking about. So when you get rid of this density because it's constant, you can eliminate it in an equation, mathematical equation. So you have only Q equal to VA. Okay. Don't worry about the derivation here. If you can get Q measure is the volume of your fluid flow per unit of time. Yeah. We call it the discharge, or you call it the volumetric flow, is your velocity time the cross-sectional entrance or area. Yeah, that's all you need to know. Procedure for analysis, a whole bunch of review, you can read that. 15.9 is on a propulsion with your variable mass. Of course, your mass is changing because you're losing it. So a control volume that loses mass, right? We can calculate this way. So that's a whole bunch of momentum, by the way. Yeah. If you pay attention, you can be able to see it. But again, don't worry about it. Okay. Just conceptual. Won't be asking. So just read only. For section 15.9. Yeah, so you have a control volume. The volume is controlled because geometrically we shape it because we want to control the flow of that fluid. Yeah, and of course they have like a different velocity, depends on the geometry of that structure that this fluid is going through. Okay, and we call that the control volume. Of course you have like a different mass right there. Yeah, moving with a different velocity. Time t, time a change in time, delta t. So time t plus change in time, there's two conditions that we're looking at it at the same time, and this is what you have. Okay, so don't worry too much about it. Just read it if you have time, and you can skip it if you don't have time. Okay, this is just showing you your free body diagram and with a rocket. Again, your control volume, by the way. Just showing you your F, right? Sum of the F, which is your sum of forces, right? Is equal to your mass and your acceleration, the whole thing, of course, for the rocket, because we're paying attention to the weight of the rocket, the velocity it is traveling, yeah, with that force. Your force is going down because you have a acceleration due to gravity pulling it towards the surface of the earth back again, but you gotta go beyond that pull force to be able to get out of the atmosphere, yeah, from the earth. So of course we also have the other parts of your velocity which is acting against that movement, yeah, which is your motion going upward. So dealing with your kinetic energy, yeah, dealing with your force, weight, and acceleration due to gravity. Okay, so that's everything that you have to know. Because that's W by G. Why do you have acceleration to acceleration? Is because this is just W by G is your mass. Okay, so don't forget it. So every time you take a look at it, you should try your best to relate to how they're relating. So if I look at it, I know that we're talking about the force, right? And that forces, you will have to balance it out because you have many different kinds of forces, which is the sum of force. Yeah, you have your kinetic energy going, you have your weight right there, and you have your force, right? Direction D going, yeah. So everything you have to take into account. And then of course your kinetic energy right there, your T, yeah, which is half mv square, and that's your ma, and the direction going down, which is d for down, and then your weight is your mg, yeah, is equal to your entire force ma, which is that. So the whole thing is your sum of force right there. Okay, for concept, you might need a little more time to actually relate to different quantities to each other. So I will definitely give you values of that you can easily solve it. Okay. Yes. And then of course you have to study to be able to see all of them all together. Yeah. Another control volume, but this time is gaining mass, right? This control volume will lose in mass right there. Yeah. This volume will gain in mass. Okay. So where do we identify that? Is because here you have time t, your change in time delta t, something happened because this is your impulse is affecting, yeah, that control volume, and here is your mass gain, because see, like change in mass I, it's just right there because of this, okay, and it goes bang. And so here is showing you the control volume that gains mass because of this impulse coming in, changing the regular, your momentum, right? And your mass right here, infinite, see, is showing you that because the change is not that much, yeah? Here is a loose, yeah? Right there, okay? You can be able to see it. Why? It's because of this impulse right there. Yeah? Look at the direction. Yeah? Don't forget that your force is very directional. It's a factor. Direction. Yeah? It's totally different. Here. Yeah? Look. This is going with it. Yes? Okay. I think you kind of get it. Just, it will take some time for you to look at it. But when you pay attention, everything is been talking to you. So the matter is just a language, yeah, it's talking to you what's going on here. So you just have to train your mind to be able to understand all the symbols, yeah, and we're playing with the symbols and factors of directions, and yes, and the motion of something moving. Anyways, in this case, you have a fluid moving, and that's your mass. A fluid moving with velocity, yes, and you always have like a one velocity and then a second velocity coming in, yes, and you always have different kinds of force acting on it, and this time is your impulse, yeah, it's just a force. We're looking at that force in a very small time, yeah, and we call it impulse. Okay, all right. This is also read through just applying your again sum of force going to your mass and acceleration thing, yeah. And here we are getting rid of we're gaining the mass, right? So reiterating this whole thing again, yes. So here going this direction, your acceleration going that direction for the mass. So this ma is your sum of mass, and you have your resistant r, and that's what's showing you. So if you take the resistant r out of the sum of force you're acting on it, constant, yeah, constant flow, then you will get the force that is going to move this fluid through that structure, yeah, and that's what it's saying. Overcome the resistance, and you'll get the flow. All right, this is a scrapper box, yeah, behind your tractor right there. It's just showing you the device that gains the mass because you are, look at this, yeah, you're taking this is your flow anyway into that structure. So the tractor is going to maintain a constant velocity because it is providing force, right, with a change in velocity within that time, little time. When that is zero, of course you have a constant velocity that tractor is using to do that motion, yeah. And the soil again is originally at rest because it doesn't move, right? The tractor is moving on it, and we are scraping the soil onto this structure. So this horizontal towing force, yeah, on that box, we call this a scrap. The structure is your scrapper box, is going to be this much, yeah. So T is equal to your 0 plus a V dm divided by dt. And that is a dm divided by dt is the rate, right? It's kind of like a velocity anyway, yeah. Change in mass divided by change in time is the rate of the soil accumulated in that box, yeah. Don't forget the T symbol, right? So this textbook is kind of tricky because it uses the same symbol for many different things. They use this for kinetic energy, yeah. They use this for thrust, and they also use this for force. So pay attention to each of the cases. Yeah, so read your problem very carefully. Okay, they look the same. Okay, then we get into review. You definitely need to know your impulse. Choose the regular equation, not the calculus one. That's my dog. In principle of impulse and momentum, yes, they're your impulse and how it can affect the particle moving with a velocity with this momentum and change, right? Of course, to a different momentum, right, with a different velocity after this impulse impacting the motion of this particle. Yeah. When this thing is zero, then you can conserve the momentums. We study linear, and we also study the impact of it, okay, where they can be able to conserve, right, momentum, because it's the same thing anyway. Yeah, when you collide the plane of contact here and moving two particles, they come into contact, but their momentum doesn't change. Yeah, before and after, it's the same thing. Yeah, so you add them up, and then you add the second one together, and they're the same. That's what it's talking about. Yeah, your particle A and B have a direct impact. The internal impulse between them is completely equal, opposite, so they cancel out each other. So we're left with the momentum, conservation of momentum. But I'm not going to ask you that, okay? I didn't even go over that, so don't worry about this. Now we go a little bit about your angular momentum and your angular impulse. Yeah. Also make sure you use the non-calculus part of it. You should be okay. And then we go into a little bit about the fluid stream. Yeah. No need to remember any of the derivation, just a concept. Yeah. For maybe multiple choice or something. And your proportion of your variable mass, how the mass loss and mass gain happen according to the structure where the impulse can affect the flow. Okay. And of course, you also have a resistance because of the structure. All right, so that's it for your chapter 15. I'm going to start right here.